not run the whole process. What I will remind you is that there isn't an integral action. So the final response should be something like this. It will be oscillating all the time, but with very small oscillation. It may take quite a long time for it, so just leave it running like this. And in this case, we can implement a fuzzy PD controller. So what are the benefits of fuzzy PD controllers compared with the conventional PD controller, PID controller? Because this fuzzy PD controller relates only to error signals and its derivatives. It doesn't depend too much on the model, Planck model itself. So if the model changes, this kind of control may also work. So it is not a quite model-dependent control strategy. So we can call it a model-free control strategy. So compared with traditional PID controllers, fuzzy PD controllers have certain properties or benefits. Apart from this kind of fuzzy PD control, there could be other fuzzy controllers. For instance, we may have fuzzy PID controller, where we still use the variables E and derivative of E, the error signal. And based on these two signals, we can establish three fuzzy inference systems for the three parameters of the PID controller. We can establish three fuzzy outputs. So there should be three outputs. And we can establish the three fuzzy inference systems for the three PID controller parameters. And then we can use a normal PID controller with variable parameters. And then in this case, we can call this kind of fuzzy controller as fuzzy PID controller. So there could be different combinations of fuzzy controllers. Here are only two examples. One is fuzzy PD. We have two inputs and one output. The output signal should be the control signal. In this case, however, if we are using a fuzzy PID controller in this way, the output, there should be three outputs, which are the parameters of the PID controller. So there could be different kinds of examples in fuzzy control systems. So another topic I'm going to talk today is the neural network and its application in data seeking problems. Before presenting this kind of thing, we have already talked about data seeking problem solutions where we have introduced something like interpolation, and also we have polynomial fit or other kind of fitting to the problem. And here I will introduce you another kind of data fitting problem solutions by the use of the so-called neural networks. So first I will explain what is an artificial neuron. And based on the neuron, I will talk about two kinds of neural networks. One is the so-called BP network, which is a feed-forward network with backpropagation training algorithm. The other one is RBF network. I will explain this kind of network for you by examples. And then I will talk about the three stages in neural network applications. One is how we can build a neural network, and then how can we train the network to such that the network will have certain expected behaviors, and then how we can generalize the neural network. So this is the topic of neural networks, and we're going to give it here. First, let's think about an artificial neuron. We say this one is the artificial one because it is different from the so-called neural system for the biological systems. So it is artificial, it is published in a mathematical way. Suppose for a signal processing unit, and this unit is a neuron. For the processing unit, there could be n input signals, and there could be m output signals. So the structure of a neuron could be something like this, and the detailed construction of the neuron is established or can be described in this way. Suppose there are n inputs. We can take a linear combination of the input by introducing n weights, W1 up to Wn. We have n weights. And based on which, and also we have a threshold here, P. With the input, weighting, and threshold, then the output of this part can be expressed like this, with the linear combination of the input signals minus the threshold. So this is a signal here. And the signal is followed by a nonlinear function. We call it transfer function or activation function. And we should have a output signal like this. So actually we should have m outputs. And this is a neuron, the mathematical description of a neuron. So in neuron, the weightings are very important, and also the transfer functions are very important. So this is a definition of the neuron. If for certain activities and certain functions, if we are trying to use data fitting, we may one neuron may not be enough, so we have to establish a neural network. Sorry, the transfer function could be functions like this. The sigmoid function and not sigmoid functions. And there could be other different transfer functions as well.